Okay, we're going to do some more stoichiometry examples. By stoichiometry, I mean we're going to take known quantities of either reactants or products and use them to predict known or unknown quantities of, again, other reactants or products. So let's see what these examples look like. In a barbecue, 15 grams of propane are burned in air. If the combustion is complete, how much oxygen will be consumed? So, propane happens to be C3H8. That's reacting with oxygen to produce CO2 and H2O. Since we've said that this combustion is complete, we don't make any carbon monoxide, CO, or any carbon. We're making all CO2 and H2O. Balancing this chemical reaction, I balance the carbons first, then the hydrogens, and then I'm left with 6 oxygens here and 4 oxygens here for 10. So 5 oxygens there. And I know I have 15 grams of that propane. Now, it doesn't make any difference in terms of mathematics whether I'm looking for another reactant or either of these two products. It doesn't make any difference to the overall actual thing that you do. I happen in this question to be looking for the oxygen or another reactant. So what I'm going to do is I'm going to take my 13 grams, I'm going to convert it to moles, because remember these numbers represent moles or the number of particles. I'm going to use the mole ratio to convert it over to oxygen, and then I'm going to work back up from oxygen to find, or with the number of moles of oxygen, to figure out the mass of oxygen gas that would have been required. C3H8. So the molecular mass of C3H8 to convert to moles here is going to be 3 times 12 plus 8 times 1. That's 44. So I've been using the equation in a lot of videos, so I'll use factor reduction method here. 15 grams converting to moles. So I've got grams and I want to convert them to moles. In 1 mole of C3H8, I have 44 grams. 15 divided by 44 is 0.341. So that's the number of moles of C3H8 that I have. I want to convert that over to a number of moles of O2. I can see that I have a 1 to 5 ratio here. So if I do that as a conversion, N of C3H8 is 0.341 moles of C3H8. Then I want to convert that to O2. For every 1 C3H8 that I have 5 O2s. So that means I have 1.7 moles of O2. Put that there. Now I want to get that all the way back up to a mass. That's what I'm looking for here. I need the molecular mass of diatomic oxygen. It should be 2 times 16, 32 grams per mole. So if I treat this as a conversion, I want to get rid of my moles and I want to introduce grams. For every 1 mole, I have 32 grams based on the fact that I'm dealing with O2. So 1.7 times my 32 gets me 54.4 grams of oxygen gas. So if I'd like to have complete combustion of propane, 15 grams of propane specifically, I need to have 54.4 grams of oxygen gas. Convert to moles, use the mole ratio to get over to the moles of the new thing that I'm interested in, and then work back to the actual measurement of that thing that I'm interested in this case, mass. One more example here. In a double displacement reaction, you want to produce 14 grams of lead-4 iodide. You'll be using lead-4 nitrate, PbNiTr, NO3. That's a 3. Oof, that doesn't look any better. Hold on. Try that again. Lead 4. See, I had the 4 in the brain. There we go. That's nitrate with a charge of -1, so I crossed over. I got 4 to 1. And potassium iodide to produce potassium nitrate, which would be soluble and just stay in solution, 4 of them, plus lead. I don't actually need that bracket. Hold on. Lead 4 iodide. That's the solid. That's the precipitate that would come in a solution. That's actually that yellow precipitate if you've seen it. I'm going to need 4 potassium iodides to make that balanced. So it says that I want to produce 14 grams of this. Again, remember, it doesn't matter if I have products or reactants. As far as the math is concerned, it can't tell which way the reaction is going or anything like that. I want to produce 14 grams of lead iodate. The question is, how much lead nitrate do I need to use? So here I have a 1-to-1 ratio. So that's going to make the mole part easy. So I'm going to go from mass to moles. Then I'm going to go over from moles over to lead nitrate and work my way back up. Lead iodide, PbI4. The molecular mass of that, lead's a big one. 207. 207 plus 4. Iodide's a pretty big one too. 126.9. I'll call it 127. 207 plus 4 times 127. $7.15. Grams per mole. That's a big molecule. So if I do this conversion here, I want to change from grams to moles. And every one, I have 715 grams. Ooh, it's big. Is that 14? Yep, 14 grams. Okay, sorry. 715, 0.01958 moles of lead 4 iodide. We have a 1-to-1 ratio, so I don't need to do any conversion here. That means for every 1 molecule of that, I have one molecule of lead 4 iodide. I have a 1 molecule of lead 4 nitrate. So if I have 0.01958, that means I have 0.01958 moles of that. I need to know my molar mass for lead. For nitrate, that's going to be another big one. Lead, again, is 207.2 plus 4 times 14 plus 3 times 16. So that is 455.2 grams per mole. So I have 0.01958 moles of that. So if I want to imagine converting those moles into grams, for every 1 mole I have 455.2 grams. Which works out into 8.9 grams of lead 4 nitrate. So don't get too... Oh, it says determine the mass of both original salts. So I have to find this guy too. Don't get too carried away thinking, do I have a product or do I have a reactant? It doesn't make all that much of a difference. Whether it's a product or reactant, you're going to use the same basic mathematical process. Okay, to get to the potassium iodide, because I didn't quite finish this problem yet. I still have this many moles of lead 4 iodide. So let's figure out how many moles of potassium iodide I have. That's good because we have a mole ratio here. So I have 0.01958 moles of lead 4 iodide. I want to convert that into potassium iodide. And that means that it's in a 4:1 ratio here. So what does that mean? Well, if I had 0.01958 of that means that I'm going to have 0.07832 moles of potassium iodide. I'm going to erase some stuff here so we can see what we're doing. There we go. Should clear us up some space. There we go. So that means I have 0.07832 moles of this. Now I want to get that back into a mass. That's the question mark I have up here. So I want to convert moles, see the moles will cancel out, to the mass. But I need to know the mass for 1 mole for potassium iodide. Potassium is 39. Iodide is 126.9. So 39 plus 126.9 gives me 165.9 grams per mole. And so for every 1 mole, I have 165.9 grams. So that means I would have had, if I multiply those out, 13 grams of potassium iodide reacting with 8.9 grams of lead 4 nitrate to produce that 14 grams that I wanted of lead iodide. So it doesn't matter if you're working from products to reactants, reactants to products, the basic system is the same. Step 1, you convert over to a number of particles, or a better way of thinking of that, moles. You use the coefficients of the chemical equation to convert from moles of one substance to moles of another substance. And then you use the molar mass, or whatever else you have, to convert from your number of moles to whatever unit that you're interested in, as all we've really dealt with is mass. What you're going to see in upcoming units is that we can use this to find out pressures or volumes of gases or concentrations of solutions or a variety of other things. So we're focused on going from mass to mass. We're doing what sometimes are called mass-to-mass problems, but it can be used in a more general sense to come up with other things too. Go to moles, or number of particles, convert using mole ratios or ratios of number of particles from one type of substance to another substance, and then convert back to mass or whatever it is that you're interested in. That's the basic approach to these problems.